Hey. All right. Now, as I was saying, all right, I need to show you for some of the to understand the pictures. I think I need to show you what they're actually maybe talking about. All right. So here's what I was saying. So here is a segment. Here's a segment. Casey, you watching? All right. Now, I'm going to try to draw the perpendicular bisector. So far, that is perpendicular. Would you agree with that?
Yes.
But it's not bisecting it. So what I'm trying to do now is I'm trying to eyeball this so it looks like that is, the blue is the perpendicular bisector. Do you agree? Right? So what that means is this now. All right? That means every point that is on here, if I were to measure from here to here, and I were to measure from here to here, it would be the same distance. Do you agree with that? Now look how easy it is to prove. Please look up, because even when you forget things, this is so easy to reproduce. Very easy to reproduce. All right. So all I'm doing is I'm making a drawing it, and it makes two triangles. And we already said it's perpendicular, and we've already said it bisects. So just by saying this is congruent to itself, I've created a what? A side angle side. So the triangles are equal. Do you agree with that? And if they are equal, then you can say that those are equal. Everybody see how simple that is? All right, very, very easy. All right, if you draw a perpendicular bisector, then every point that's on the perpendicular bisector is equidistant from the endpoints. Is everybody understanding that now? All right, Casey, you good now? All right. Now, what I want to do now is I want to try to draw a triangle for you real quick, and I want to try to explain, because we used to do constructions, but because of the amount of time that it takes, I kind of skipped that particular part of the lesson. But look up, please, so I can show you now what is meant or what's important about this particular section. All right, I'm now going to draw the three perpendicular bisectors of that triangle. So normally what I like to do is I like to just draw something here, and I try to first make it perpendicular, and then I try to move it so it bisects. All right, so what I'm showing you now is this is perpendicular, and that's equal to that. Is everybody good with that? All right, now what I want to do is I want to do the same thing for the other side. I'm trying to draw something perpendicular. That looks perpendicular. Now I'm trying to make it so that it bisects. That looks kind of good. All right. So from there, that would be true. All right. Now I'm going to draw one more. All right. And when I draw one more, first try to find that it's perpendicular, and then I move it so that it bisects. And that would be perfect. All right, so now watch here, please. Look up on the board. All right, so what I've done is I've drawn the three perpendicular bisectors of that triangle. All right, now this is kind of how I want you to try to remember it. So please stop doing what you're doing. Some of you guys are trying to get the work done. I don't care about the work. I want you to listen to what I'm saying, because it's super easy. But I say that every year, and people don't hear what I'm saying. All right, so it's not going to be easy for you unless you're listening to me. This point right here, where all three lines meet, is called a point of concurrency. That just simply means where the three lines intersect at a single point. All right, now what is fascinating about that? Please watch. And again, I don't understand why it's so difficult. If you're on the perpendicular bisector, then you are equidistant from the endpoints. Do you agree with that? Do you understand what I just said? If you're on the perpendicular bisector, you're equidistant from the endpoints. So now what I'm trying to do now is I would like everybody to please watch. If I draw from this point right here to this point right here and to this point right here, what can you tell me is true? That this right here, this point right here is the same as that point, that length right there. Does everybody agree with that? What? All I want you to do is just list yes or no. That's all. It's a yes or no question. Are those equidistant from the endpoints?
Is the green two lines equidistant to the red two lines?
Can you come on? Come on, Zoe. All right? That means you don't understand what I just stated 10 times. You understand what I'm saying? All right? Now, the two green lines are on the are drawn from the perpendicular bisector. Now what I want to do is I'm going to keep it green and I'm going to draw from here to here. Now what's true? These two here now, come on, look up. This right here is congruent to this over here now. Does everybody agree with that? Then if I draw this here and here, because it's on that perpendicular bisector, what's true now about this line right here? Let's see if I can do this. What's true about this line right here, this line right here, and this line right here? They're all congruent. That is exactly correct. Because why? Again, it's where all three perpendicular bisectors intersect. And what I'm trying to establish is, like I said, I'm not sure why people find this so difficult. All this point right here is called the circumcenter, and it is on the perpendicular bisector. Now, it just so happens that that's the perpendicular bisector for what? All three of those parts. Am I making sense? So if I were to draw from that point to each vertex, that forces these two to be the same, and it forces these two to be the same, and it forces these two to be the same. So then they're all what? They're all the same. All right, that's all that means. All right. Now, something kind of interesting to that, if for example, they're going to give you a story where, you're at this building over here, and this building over here, and this building over here, and you want to be equidistant from each building. Is it possible to figure out that point? Yes. All you do is draw the what? Three perpendicular bisectors. All right. So there is some practical application to this. All right. There is some practical application to this. All right. If you want to find a point that's exactly the same distance from the three vertices of a triangle, you can find that by simply constructing the perpendicular bisector. All right. Is everybody with me on that? All right. Hopefully that makes sense. All right. So again, the point where they all intersect, all three lines intersect at the same point, is called a point of concurrency. And in this case, when you draw the perpendicular bisectors, it will be equidistant from the vertices, and it's called the circumcenter. Very simple. All right. We're also going to do one for the angle bisectors, for the medians, and for the altitudes. All right. But now, if you flip the page, all right, I got to show you something else now. Now we're going to do the angle bisector. All right, we're going to do the angle bisector. So kind of look up here on the board. All right, where I'm going to draw an angle, and then I'm going to bisect it, and I want you to tell me what's probably true. All right, so if I draw an angle, now what I'm going to do is I'm going to try to bisect this angle. Stay with me. Try to bisect. Perfect. All right, so I just bisected that angle. All right, So I just cut it in half. Now, I know that this angle is the same as this angle right here. Now, I'm going to pick a point on the angle bisector. And now I'm going to draw the distance from that point to the side of the angle. Now, I need everybody to look up here because to me this was kind of obvious, but for some people it was not. If I measure that distance from here to here, is that the distance? Is this the distance? Is this the distance? Which one of those is the actual distance? Who can tell me? How do I figure out the distance from a point to a line? Why is that the distance and none of the others? It is the perpendicular. Perfect. So when somebody asks you the distance from a point to a line, you say you're going to find the shortest distance. And the shortest distance is the what? The perpendicular. Everybody pretty happy with that? Right? So this is perpendicular. Do you agree with that? All right. And then down here, all right, if I draw here, that would also be perpendicular. Does everybody agree?
Yes, sir.
Right. Now the question is, what do you think is true about this measure and this measure? They are definitely congruent. All right, they are definitely congruent. Now, how do I know they're congruent? Well, there's lots of ways. If two angles of a triangle are congruent, then the third angle is congruent. So we could automatically say that this is congruent to this angle right here, and then you have angle, side angle, you have side angle, side. There's all kinds of different ways. Everybody see that, though? Easy, very, very easy to prove. Very easy to prove. So what are they telling you now? They're telling you now that if you are on the angle bisector, you are equidistant to the what? To the sides of the angle. Is everybody happy with that explanation? All right. If you're on the angle bisector, then you are equidistant to the sides. All right. That's the next big lesson. All right. Now, how is that helpful in a triangle? So in the interest of time, what I'm going to do is I'm just going to come up here and erase this real quick. And I'm going to show you what happens if I draw the three angle bisectors. And like I said, they're going to ask you to prove this. But again, if you pay attention, you won't have to prove it because it's just so obvious, all right, about what they're trying to prove. So what I'm going to do now is I'm going to construct the three angle bisectors. Uh-oh. So if I try to draw the three angle bisectors, here we go. All right, that's an angle bisector. And how do I know that's an angle bisector? Because I just looked at this and I said that angle is about the same. Now what I'm going to do is I'm going to try to find the angle bisector here. I'm going to draw the angle bisector, and that looks about correct. And then what do you think is going to happen? I'm going to draw the third one, and guess what happens? You create, there is exactly a point of concurrency. So please watch here. So these two angles are equal, and then over here, these angles are equal. Now, are all those angles equal? No, they're definitely not equal. All right? So this, again, is called a point of concurrency. That is called a point of concurrency. And you get the point of concurrency on this is called the end center. It's called the end center. Now, what I want to do now is I want you to see if you can understand why I say this is so easy. All right, if I'm on this angle bisector, that means this distance from here to here is going to be the same as the distance from here to here. Do you agree with that? Right, and again, look up. That is, again, perpendicular here and here. And then, because I'm on this angle bisector now, I'm on this angle bisector right here, then I'm also going to be equidistant to this. So now, what's true about all of those? They're all equal for the same exact reason. All right? So this distance right here is equal to this distance right here, which is equal to that distance right there. So if you are trying to find, for example, the side or a point that is the same distance to all sides of the triangle, you would be finding the angle bisectors. And the angle bisectors are called, it's called the incenter. Now, why is it called the incenter? Actually, because it's inscribing a circle. If I were to draw this perfect circle there, that would be inscribed in that triangle. So it is possible to find exactly a point that touches all three sides of the triangle. And we say that it's tangent. And what does tangent mean? Tangent just means it touches at exactly one point right there, and it touches at exactly one point there, and one point there. This distance right here is considered the what? The radius of the circle. Is considered the radius of the circle. The other point that I drew, see if you can listen to me for just another minute. All right? The other point that I drew was called the circumcenter, which if I took that point, I don't remember where it was, but I'm just going to try to show you. We said this was equal to this distance here and to this distance here. Then what happens is we say, the circle here a bunch of shh. All right. Perfect. You're welcome. All right. So we say that one is inscribed, the circle on the inside is inscribed, and the circle on the outside is circumscribed. All right, so one circle goes on the outside, one circle goes on the what? Inside. And what you have to understand is that the one on the inside is found by using the angle bisectors. The one on the outside is used by drawing the perpendicular bisectors. All right, now I believe that is a summary of everything. Except if you look at one more thing on page 326. All right, I'm not going to ask you this. All right, because I just think it's just pure memorization and I don't really care. All right, if you look at the circumcenter on an acute triangle will always be on the inside. All right, and obtuse, it will be on the outside. And if it's a right triangle, it will be on the hypotenuse. So again, those are just some little fun facts for you to ponder. But now, what I want to do now is I just want to flip over to the actual questions. All right, so here we go. Now, just to show you again what I mean by how simple it is, let's now look at the questions. All right, so here we go. Look right here. Now, you have to identify XZ for question number 1. Look up. XZ is called a what? Perpendicular bisector. Because you've established it as a perpendicular bisector, then XW is obviously what? 12. So number 1 is 12. Honestly, it's really and truly this simple. All right, it's very simple. All right, and especially if you listen, by the time we get to the end, there's going to be a lot of simple things, and a lot of people don't do as well as they should on this test because they think it's so simple. They don't review the rules. So make sure you're concentrating with me on the rules. All right, number 2. Is that a perpendicular bisector?
Yes.
Yes. So AC would have to be what? Yes, AC is definitely 14 because we know that DC is 7. Hey. All right, now number 3. All right, again, this is the perpendicular bisector. So we should be able to just look at that. Everybody should be able to look at that and just say X equals 2. All right, now practice your mental math and make sure that is correct.
Yes.
All right, So now, if we figured out that x is equal to 2, we should be able to tell me that LP is equal to 15. All right. LP is 15. All right, now let's take a look at question number 4. Here we go. It says, 4 friends are passing out flyers at a mall food court. 3 of them take as many flyers as they can and position themselves as shown. The 4th one keeps the supply of additional flyers. Copy the position of A, B, and C, and then position the 4th friend D so she is the same distance. I don't really care about that. Right? What I care about is that you can tell me if you were given A, B, and C and you had to position somewhere right in the middle of all 3 of them, you would simply find the what? What type of point of concurrency, though? The perpendicular bisector. All right? Because you want to position yourself so that AB, so the distance from A to D is the same as from B to D is the same as from C to D. So in order to do that, you would actually have to create a triangle ABC. So bear with me. All right, no, you know protractors. All right, again, listen, let me explain. In the past, what we've done is we've actually done the constructions ourselves using a straight edge and a compass. All right, but we're not using that. All right, right now we're just kind of saying that's what we would be doing. All right, so right now we would be constructing the 3 perpendicular bisectors. All right, now let's check out number 5. CP has to be what?
CP has to be
8. Again, because BP, we say, is the angle bisector. All right? Let's look at number 6. So WYZ would have to be what?
67.
Good, 23 degrees. All right?
3,000. No one was asking for me, so it's bad.
All right, number 7. All right, again, it's the angle bisector. So if we solve this, we say x equals what, guys? I got x equals 5. And if x equals 5, then QM would be what?
12.
QM would be 12. All right. Now let's take a look at number 8. All right. Make sure in center. All right. You have to identify and you have to understand what is the in center.
Inside
All right.
circle.
The inside circle. That's right. In center for inscribed. And inscribed means you're the angle bisectors. You're the angle bisector. All right. If you are on the angle bisector, then that means you know you are equidistant from the sides. You are equidistant from the sides. So in this case, QM is how much? 9. So PQ is also what? And QK is also what? 9. Now, it's asking for JQ. So how would we find... Now, listen to me. JQ right here, this length right here, be careful. All right? It's not something that's congruent to the other ones. We would just simply have to do what theorem? Yes. All we're doing to find JQ is we would say JQ squared is equal to 9 squared plus 16.5 squared. All right, so somebody take out their calculator and go ahead and do. So JQ, you're telling me is about, is it?
Wait, no. It's 18.79.
Yeah, so I'm okay. 18.8. All right, it's 18.8. All right. Now again, a lot of the work is dealing with right angles. So a squared plus b squared equals c squared is going to be kind of important. All right, any questions with that? All right. So honestly, I think that's it.
Where's the incenter?
Angle bisectors. So your job now is to finish up. You're doing, mark this at the top of your paper just to make sure. 1 through 14, 17 through 30, 41 and 42. Those are the problems I'm asking you to do. One more time. 1 through 14, 17 through 30, 41 through 42. I think I've sent out the solutions already just in case some of you have a little issue. All right, please look up these solutions.
I thought it was not